and congratulations for making the early session. So I will be talking about the VinRouge survey. So we can all agree at least that we have a cool acronym. I also would like to say that I'm speaking on behalf of the PI of the survey and of the entire collaboration. Neil Tanvir could not be here today, so anything insightful that I will say is his credit, but if I make mistakes, it's my fault. This is the entire collaboration, and like VinRouge is a bit of a different service compared to many other of the surveys at Vista and VST. The target, the goal, is to discover the electromagnetic counterparts, so whatever emits light, and specifically infrared, to gravitational wave sources. In particular, those due to mergers of neutron stars, of binary neutron stars, or neutron stars and black hole. This is a recent study, relatively recent field of study, which is opened really in the last decade, and there are huge implications in various aspects of astrophysics, including, perhaps more importantly, the nucleosynthesis of heavy elements, which is still not all the heavy elements are fully accounted for. We don't know their origin in the cosmos. There is a lot of range of studies about neutron stars, their equation of states, and the nuclear physics that regulate the behavior of neutron stars. There is always an application to the measure of the Hubble constant. There is also a connection between the merger of neutron stars and gamma ray burst, which emit relativistic jets. So we can observe the mechanisms of jet launching. We can connect these two components. Also, like the study of these systems, these binary neutron stars or neutron star black hole systems, of course, come from stellar population. So there is a lot to be learned on how massive stars evolve in binary systems. There are also like more fancy applications, for example, limits on the speed of gravity compared to the speed of light by observing both the gravitational wave and electromagnetic radiation. And of course, probably there is more that here is not mentioned. So this is a movie that I hope will play properly. And here you see two neutron stars that are in spiraling. They are close and they emit gravitational waves which these yellow waves represent. And as they close, you can see that their spherical shapes start to deform and they merge together. And in this process, crucially, they emit you saw the ejection of a material, and some other material stays and forms an accretion disk. So these two phenomena that you saw, the tidal material tidally ejected and the accretion disk, is what makes these explosions electromagnetically bright. A lot of energy is released in gravitational waves, but still there is a component which of material that is ejected. So these are also transient. They are called kilonovae. These because their luminosity is roughly 1,000 times that of a nova, and so they are fainter than the supernovae, which are of course explosion of massive stars. So I'll let this video play a few times. It's quite interesting. Here you see the elements, so in the atomic number on the x-axis and the proton number on the y-axis. So you can see that there is a zone of stability. These are the nuclei that we know and that exist are more or less stable on Earth. But in this is a context in which the neutron stars are the material which is being ejected is full of neutrons. Is basically up to 50% of neutrons. And so what happens is that the intense neutron flux creates heavier and heavier nuclei, and I'll play the video again. Or try to. Yes, so basically, immediately you form nuclei which are very far away from the stability zone. They have many more neutrons than protons, and you can create very, very heavy neutrons. Very, very heavy nuclei, and these are of course highly unstable, so they will decay via beta decay or via fission, and in this decay will end up forming the stable elements. And so this is basically why this environment is so attractive, because you have a very high intense neutron flux in which you can build up the high atomic numbers, which are not produced in supernovae. And this is what is called the R process. R means rapid, and that means that the neutron flux is so intense that you have a high likelihood to get invested by a new neutron before decaying. So like a new unstable nucleus is formed and immediately is transformed to another unstable nucleus by accreting more and more neutrons. So this is the rapid, because these nuclei do not have time to decay before climbing up the ladder. And so like all these nuclei are created and they are unstable, they will decay, and their radioactive decay, a little similar to supernovae, will power the emission of the kilonova. So here a crucial element or a crucial point, these elements are very high atomic number. They have a once they cool enough to become atoms from nuclei, so to recombine with the electrons and become atoms, they have a very, very rich structure of levels. They are not like the lower atomic number elements, which have discrete sets of elements. So basically, they provide a very, very high source of opacity. There are so many transitions that they create basically, and coupled to the velocity, all lines, all levels are broadened by velocity. So basically, they create an incredibly strong opacity. So basically, the expectation is the light will be emitted only in the infrared, which is less opaque. So the detection of kilonovae has always been thought as prominent in the near, and the emission will stay longer in the near. Yes. So at this point, you can understand why VISTA is a good survey telescope, because of course it is sensitive to the near infrared, and it has also a large field of view. So it's ideal to detect these explosions. The VinRouge survey is not is a small survey compared to other, and it just it doesn't follow to cover a specific area of the sky, but whenever there is a new gravitational wave event, it will follow up the uncertainty region provided by the detectors. So like also there is an advantage that to look, but I'll speak about this later. So so the strategy of the survey is very different. It's a bit haphazard. Like whenever there is a new event, a specific portion of the sky has been targeted depending on the visibility at the moment. So we have to cope with the unexpected of a target of opportunity. So something that has come up non-planned. And basically, for each event, the survey has targeted about 30 square degrees in each of the detected events. It's a very important thing that the VHS survey and other VISTA surveys have already provided a map of the sky in the infrared, especially in the southern hemisphere. And this is crucial because to locate a kilonova, you need the reference frame to see that there is a new object that wasn't seen in archival images. So it also benefits very much from the other VISTA surveys. And just to say that the gravitational waves are unfortunately come with very large errors. So these are three cases from desperate to typical to optimistic, in which you see that these are a map of the sky. So like even in good cases, we are speaking of 300 square degrees of sky to survey, which is not only difficult because it takes time, but it will also contain a large number of unrelated transients which have to be filtered out. So one strategy to try to reduce the amount of data and the volume of like sky area to be imaged is actually to convolve with known galaxy surveys, because these neutrons. So first, the gravitational wave detectors provide the redshift, or actually distance, as a matter of fact. So and also we expect binary neutron stars to be associated with galaxies, and especially massive galaxies, because they will have a higher number of objects. So basically, if we know the distribution of galaxies in a certain direction of the sky, we can skip regions that do not contain significant mass. So if we know that the gravitational wave event is at 100 megaparsec, we will select only galaxies which are within a certain tolerance of 100 megaparsec, and we will skip tiles in the sky that do not have any. So this is a way to cut down both the area to be served and especially to cut away many transients that will be unrelated. So this is the timeline of the gravitational wave detectors. So basically, the survey could only function when these were in operational, and you can see that there have been like 4 observing runs, or 1, or 2, or 3, or 4. And these are the 3 gravitational wave detectors which operate, even if CAGRA currently does not provide really constraining information. And so this basically started in 2015. So as you say, it's less than a decade old story. Now we are in the actually maybe 1/3 in the 04, the 4th observing run. But the VinRouge survey was live during the 2nd and 3rd runs. So in 01, I mean, this, even if you are not in the field, you must have heard about this. In 01, there was the first discovery of a gravitational wave events. This came from a binary black hole of very large mass. This is the strain, the oscillation of space-time, in a sense, provided by the observatories, the LIGO detectors. There was a Nobel Prize. It was a fantastic moment for physics and astronomy. So at the time, actually, this was before the Ultravista, sorry, that's the VinRouge public survey. So that was a pilot program. So we, in this very large uncertainty region, Vista observed a fraction. And actually here you can see that unfortunately the positions are subject to revision. So some of the tiles that we took were basically not necessary. All these regions are the tiles, while the orange contours are the localization uncertainty from LIGO. So basically, we covered some tiles with the hope to find some object. So to be honest, like this was mostly a test of the system, a stress test of the system, because for binary black holes, we do not really expect counterparts, electromagnetic counterparts, basically because there is no matter. In the black holes, you have the 2 black holes with their event horizon, they merge, they emit a lot of gravitational waves. We're speaking more than, I think, several solar masses in energy, so M solar mass is C², but there is no matter, basically. There's nothing which will shine. So we don't, in general, expect to detect electromagnetic radiation for these events. But of course, well, you never know. This was the first event, so there was a big. Many in the community joined this campaign, and Vista was also in this, let's say, review paper where all the observatories reported their non-detections. In fact, in 02 was also. Actually brought the second big surprise. There were 8 gravitational wave events, of which 1 was actually a binary neutron star merger. But the first that we observed was a few days before. There was a 90 square degree error region, and Vista did make some follow-up. We were again in the phase of testing our capabilities, which actually 3 days after were put to actual real test, because in this case, there were neutron stars. So if you have a neutron star, you have matter, and that is what can emit light, and what we saw from the simulation, there will be emission. And so this was also very coincidental. The third gravitational wave detector had just joined a few weeks before, so the network was in full operation and allowed to locate this event. And you can see that compared to others, this was much more tightly localized. And maybe everyone has seen these pictures sometimes. So this would be the gravitational signal, the so-called chirp. I should have put the sound because you can transform into a sound. And immediately after, there was also a gamma ray burst, 2 seconds, 1.7 seconds after. So this cemented the connection between gravitational waves, binary internal mergers, and short gamma ray bursts. That had been speculated for many, many years, but it got a spectacular confirmation. So this is, again, a map of the sky where this is the uncertainty region of the gravitational wave. This is the uncertainty of the gamma ray burst, which unfortunately was not very much constraining in this case. But by selecting these galaxies that were consistent with the distance implied by the gravitational wave detection. So you can see that even inside this big error box, we could select the regions of high probability was much smaller region. And so in the end, the VISTA observed only these 2 regions, and the counterpart was discovered not by us, by another telescope, but VISTA had pointed independently, and the source is there. And it lies in this galaxy at 40 megaparsec away. The counterpart is this object that you can see fading. And here you can see the light curves, where the red is the K band, and then we have the J band and the optical band. As you can see, now that it develops, the K band, the infrared, stays bright and much observable for much longer compared to the optical data. Even if VISTA is also like not like a 4-meter telescope, even the big mirrors were not able to follow it more longer than the expected time. And you see, this also event confirmed our hypothesis that the kilonovae are associated with big massive galaxies. So this was one such galaxy. And so looking close to that is perhaps a good strategy. And these are also some pictures showing the 6 telescopes that actually simultaneously discovered this object. You see the counterpart, the VISTA is one of them. The SWOP was the first one in the optical. There was also X-ray detection, there was radio detection. This was a very spectacular campaign. ESO participated in full swing. And this is actually some nice pictures prepared by Boumil van Gessen, who is sitting here in the front. And you can see the kilonova in the various, these are various epochs, and you can see that it's coming from blue to red. This is well, even blue means this is a KJY, so all infrared, but you can still see the reddening with time. And these are like very much zoomed, where you can see much better the change in color in a visual manner. Actually, this is the light curve that I showed before, and so the modeling of the light curve gives a lot of information. The kilonova, it allows to determine the ejected mass, which basically, if we assume that this is a heavy element, also gives us the yield, how much heavy elements these objects produce. So these are key and crucial characteristics. And VISTA basically provided the majority of the existing near-infrared photometry for this event. Okay, this is a very dense slide, but basically it was amazing how this event offered a glimpse of all the components that had been predicted, like the gravitational waves coming from the spiral, the gamma ray burst produced in a jet launched by the merger, and the kilonova with the formation of our process. At late time, we could see actually the jet slowing down in the interstellar medium, and actually this is fairly impressive. This is from August 2017. This event is still detected to date in radio and X-ray observations. So this late radio data allowed even a better characterization of the physics, of the geometry of the various components. It's a complex system that you have. It's actually close enough that the VLBI was able to detect both proper motion at 40 megaparsec. This is a superluminal proper motion, apparently superluminal, that is a confirmation of relativistic motion. And so the source was moving, but was also unresolved. So that means it was compact, and this allowed also to disentangle between various models. Here you can see a jet, here you can see different geometries which would be had a larger angular size that would have been resolved. And So basically, the discovery of this event has an implication for a lot of branches in the field. So the discovery from Vista or from all the service has a incredible trigger potential to facilitate, to enable many kinds of different physics. Okay, here also it explains that there are more components. It's, as I said, it's a different structure. Basically, the key thing that if you want to remember something of this complex physics is that in the merger you have an accretion disk made of nuclear matter, and this irradiates neutrinos. And these neutrinos will interact with the ejecta and alter the ratio of proton to neutron, and this has deep impact on the nucleosynthetic products. So the more neutrons you have, if you have only neutrons, you will more easily create all the heavy atomic numbers by this process that I described before, in which you create more and more neutrons and you go up in mass number. But if you convert some of the neutrons in protons via interaction with the neutrinos, then you will not create the heaviest element. You will stop at some point. And so the precise interplay between these parameters allows actually diversity of nucleosynthetic products. So this was basically the highlight of O2, in which there was the first discovery of a binary neutron star merger with a kilonova. O3 extended it from 2019 to, well, the pandemics, so 2020. It was incredibly more sensitive, and you see that we have, in O3 we had 90 mergers, while in O2 we had 8, so it's a order of magnitude. Unfortunately, so there was only one binary neutron star merger, and it was much more distant. I'll mention it in a minute. There were also neutron star plus black hole mergers, so a new kind of system that had not been discovered previously. So this is the binary neutron star merger system. However, it was a bit cursed, if you allow this expression. The area, the localization was really bad. The visibility of the area was even not easy to do from ground. So basically, there was no counterpart detected for this object. So no luck with this. And this is actually only the second binary neutron star mergers that was detected. So for now, we have a 50% success rate. I don't know if you can call it, but we certainly would like to have more. VinRouge also followed another event shortly after because it looked at also to contain a neutron star. Unfortunately, it was subsequently retracted, not considered significant enough over the background of gravitational wave noise. This is quite an interesting system. So this is a neutron star plus black hole merger. So this was the first clearly recognized, and it has a highly asymmetric mass. So you have a 23 solar mass black hole with, well, to be fair, it's a 2.5 mass solar masses object. We don't know if it was a neutron star or a very small black hole. We don't know any black hole in that mass range. So we suspect it was a neutron star plus black hole. So here we carried out Vista, teamed up with other observatories to look for a counterpart. And there was a big campaign also with Engrave, which I'll mention later. So basically, there was no counterpart also here. And one conclusion of this non-detection is that probably the neutron star was not disrupted, but was entirely swallowed by the black hole. So there was no ejection. The black hole was so massive that basically it got the neutron star without ejection. And in this case, again, you don't have any ejected matter, so there is no light. So O4 is currently ongoing. There are 2 LIGO interferometers plus Virgo, in parentheses, because unfortunately it is experiencing some technical difficulties, and Kagra is still developing. It has a long way to go. And I have to say this has been a little unnerving, because since May there has been not a single binary neutron star merger. So this unfortunately is indicating that the volumetric rate of neutron star mergers in the local universe is not very large. It was not known precisely. So of course this limits a bit our chances to detect a new object. But I don't know. Maybe when I finish this talk, I will go and I will find an alert from the next binary neutron star merger. So I'm optimistic. And of course, this field is in extreme expansion. Beside an already scheduled O5 run that will be in a couple of years, there are new instruments being studied and deployed, brought from ground and from space. The Einstein telescope should be the next marvel in the gravitational wave detection, and it's being discussed, and it's become a key project in several countries. It's not yet funded, but it's clearly has gotten very much momentum. And of course, the Vera Rubin telescope will also provide a great hand to survey the gravitational wave error regions. Just a mention about the impact. So this is actually, okay, this is a picture of a slide that was showed a few days ago. So I'm stealing it from Magda Arnaboldi's talk. So if you can even see, the publication of VinRouge has been very, very much smaller compared to others. Because, well, we did every survey that we could, every event that was meaningful to do. But with a bit of interest, I have to say that in terms of publication, you can see that the dark orange histograms are the publications. Citation, sorry, of course, my bad. So the citation per paper is actually like unrealistically large. This is because some of the papers were incredibly high, like the papers in collaboration with the entire community has like a large number of citations. This was all the electromagnetic community merging together to provide the best possible data set. But even the paper on the kilonova data from Vista is faring very well, I would say. And also in terms of outreach, there was a big splash when this happened with the press release at ESO in the US, and so like these events catch a lot of the attention. So I expect that also next events will also be very well received by the public. I did mention, because like cosmology is always there is always seen that gravitational wave detections allows also to measure double constant, basically because you can measure the distance from the intensity of the gravitational wave signal by modeling it, and you can measure the redshift, so you have two independent distant measurements, and you can try to. So like with one event, of course, this is way not constraining compared to the thousands of supernovae used or the CMB and so on. But if we could increase the samples significantly, that would allow a completely independent double check also with the cosmic crisis of the discrepancy between the two measurements of H naught. I would like to finish with something that is perhaps new and interesting, like that while there is not so much detection of kilonovae by gravitational waves, we found out a new way to pinpoint them. So I mentioned before that gamma ray bursts also are associated with binary neutron star mergers. And in the last couple of years, we detected a couple of systems extremely interesting and relatively nearby that allowed basically to detect the kilonova. I won't go in too much details, but basically this gamma ray burst once produced the light curve in which also there was this very distinct feature of the extremely red infrared bright object not visible in the optical, and basically modeling reveals a very similar object to the 1 kilonova from 2017. This was very unexpected because this kind of GRB was not suspected to be associated with kilonovae, but we had to accept that there is a new channel to make kilonovae. And very recently, this is a paper due to being published Wednesday, I believe, there was another kilonova detected in connection with the gamma ray burst, where you can see, like, I don't know if you can see the kilonova indicated is obviously the reddest object in the field, like it's unmistakable. If you maybe I should zoom a little bit, and this was observed actually with the James Webb Space Telescope. This beautiful galaxy that happened to be face on is very likely the host galaxy. So the system was ejected by this galaxy because to form a binary neutron stars, you have two supernovae that have to go off and impart a kick that in the time where the system will merge, the galaxy the system can travel tens of kiloparsecs from the host galaxy. But the spectacular thing is that, again, we took spectra in which we could detect some of these heavy elements. So the interpretation is very tricky and it's model dependent, but in this case, the model suggested tellurium, the detection of tellurium in this spectra. So this GRB channel opened a second avenue to detect and study kilonovae, so it's quite good. And this is the first object for spectra, the first object from 2017, the one also observed by VISTA. This was a VLT spectroscopy, which allows to detect strontium and also yttrium. And now, well, this is a very preliminary, but there are about 20 elements who have been claimed to be detected in the spectra of this kilonova. So just to conclude, this is, I think, is my last slide. So ESO has been involved a lot in like via the VinRouge program, but is now involved also in the follow-up program. The ENGRAVE collaboration is a follow-up program that has included the majority of the European astronomers in this field. It's about 250 scientists. You can imagine how easy and smooth is the management of this collaboration. No, it's actually surprisingly positive. And we have a very an ongoing ESO large program, and we are waiting for the next kilonova. At the same time, there is also a program, I have to mention it because this program is the one that is paying my salary. And so this is a joint theoretical, theoretical, experimental and observational program to detect this, to study the spectra of the kilonova and to study specifically the deformation and the enrichment of the universe in heavy metals. And I think that shall be all. I don't know how am I doing with the time.
We'll have 3 minutes.
If there is any question, I'll be happy to take them in 3 minutes.